Let's take on some more questions from the chapter Torsion of Shafts in this video. A shaft with a circular cross section is subjected to pure twisting moment. Okay, the ratio of the maximum shear stress to the largest principal stress is, okay, for pure shear stress case, the Mohr's circle can be drawn like this. I have explained this in the on the previous videos. This is the Mohr's circle for the case of pure shear stress. Okay, this is what sigma 1, this is what sigma 2. Sigma 1 is equal to sigma 2, is equal to actually minus of sigma 2, but their magnitudes are equal, and this is tau max. So tau max is equal to the radius of this Mohr circle, and the largest principal stress is also equal to the radius of this Mohr circle, so their ratio will be 1. So the option is B. Okay, next question. Okay, do try this question before seeing the solution. It's a good question. Okay, if you have tried the question, a machine element xy fixed at end x is subjected to an axial load P, transverse load F, and a twisting moment T at its free end y. The most critical point from the strength point of view is, okay, see the options: a point on the circumference at location y, a point at the center at location y, a point on the circumference at location x, and a point at the center at location x. Okay, so let's draw the stress distribution for the axial load, I mean due to axial load, due to transverse load, and due to twisting moment. Okay, so stress distribution due to axial load will be this. Why? Because the axial stress will be uniformly distributed over entire cross section. Okay, axial stress distribution. Okay, what about the torsional shear stress distribution due to this torsion? It's like this. You've studied this in your theory portion. Okay, that the torsional shear stress is maximum at outer periphery. Okay, so torsional shear stress. Okay, and what about this transverse load F? This transverse load F is actually going to create a bending moment at X, not at Y. Okay, so A and B options get rejected. There will be no bending moment due to the transverse load F at Y, but there will be an additional bending moment at X. So A and B can't be the options. Okay, now you have to see that at location X, the most critical point from the strength point of view is a point on the circumference or a point at the center. Okay, so the bending stress distribution due to this load F, transverse load F, is again like this. You have studied this. Okay, this is passing from center. Okay, it is also maximum at the top and bottom fibers. Okay, so add all of them. Okay, you will see that the most critical point from the strength point of view is a point on the circumference at location X, because the maximum stress is present there. Okay, this was a nice question. Okay, so the next question is, two circular shafts made of same material. Okay, the material is same, one is solid and the other one is hollow, have the same length, L is same, and polar moment of inertia. Okay, So the polar moment of inertia, that is J, is also same. Okay, both are subjected to same torque. Torque is also same. Here theta is the twist, and tau s is the maximum shear stress in the solid shaft, and similarly theta h is the twist and tau h is the maximum shear stress in the hollow shaft. So we have to find the relations between both of them. So obviously we'll be using the torsion equation, that is T by J is equal to tau by R is equal to G theta by L. Okay, so let's compare these two relations first. That implies T by J is equals to tau by R. Okay, so tau S is the maximum shear stress in the solid shaft, and tau H is the maximum shear stress in the hollow shaft. T is same and J is same. T is same, J is same, so I can say that tau max is directly proportional to the radius of the solid shaft and the hollow shaft. Okay, so suppose this is the hollow shaft. No, let it be the solid shaft. Okay, this is the solid shaft. Its diameter is ds. I have denoted the diameter by ds. This be a hollow shaft. Okay, the inner diameter is di and the outer diameter is do. Okay, so as J is same, okay, the outer diameter of hollow shaft has to be greater than the diameter of solid shaft, because J is same. See, pi by 32 ds raised to the power 4 is equals to pi by 32 d naught raised to the power 4 minus di raised to the power 4. So for this equation to hold valid, diameter of hollow shaft do has to be greater than ds. Okay, so this is the condition. So tau max is directly proportional to d by 2. Again, this is a constant, so whichever shaft is having the greater diameter will be actually having the maximum shear stress. So the outer diameter, because in this relation we write the outer diameter, so the outer diameter of hollow shaft is greater than solid shaft. That implies th must be greater than ts. Okay, and for the angle of twist relation, let's equate T by J is equal to G theta by L. Okay, so T is same, J is same, TL by GJ is equal to theta. T is same, T is same, J is same, L is same, and G is also same because they are made of same materials. Theta is actually independent of D, so this will be the answer, that the angle of twist in hollow shaft will be equal to the angle of twist in solid shaft. So the options that satisfy our answer are theta d. Okay, theta is equal to theta h and tau h is greater than tau s. So the option D will be the answer. Next question. A hollow circular shaft of inner radius 10 mm. Be aware that this is radius which has been given to us. Let us write diameter. Di is equal to 20 mm here only to avoid any mistake. So outer radius is 20 mm, that is d outer is 40 mm. Okay, because generally we deal in diameters in our formulas, so write the diameter here only. And length is 1 meter, L is 1 meter, is to be used as torsional spring if the shear modulus G is 150 gigapascal. The torsional stiffness of the shaft is, okay, so you know that torsional stiffness of the shaft is given by relation Gj by L. Okay, G is given to us, that is 150 gigapascal, that is 10 raised to the power 9 pascal. L is 1 meter, and J, what is J? For hollow circular shaft it is pi by 32. pi by 32, d outer raised to the power 4 minus d inner raised to the power 4. Every value is given to you. So 150 into 10 raised to the power 9 into pi by 32, d outer, that is 0.04 meter, okay, raised to the power 4 minus 0.02 raised to the power 4. So this is our answer. So whatever be the value, this will be 35342.9 Newton meter. Okay, before filling, check in which units you have to fill. Oh sorry, Newton meter per radian. So before filling the answer, check in which units you have to fill the answer, and it is kilo Newton meter radian. Okay, so that will be 35.342 kilo Newton meter per radian. Okay, so 35.342, this is our answer. Okay, correct to 2 decimal places. Even if you fill up to 3 decimal places, it will not be, I mean, you will not fetch negative marks. Okay, if your answer lies in the range. Okay, so let's take on the last question from this chapter, torsion of shafts. A bar of circular cross section is clamped, ends P and Q as shown in the figure. Okay, they're clamped actually. Yeah, so a torsional movement of a torsional moment T is equal to 150 Newton meter is applied at a distance of 100 mm from end P. Okay, the torsional reactions TP and TQ you have to find. So again, a pretty simple question. This is our circular bar, and a torque 150 Newton meter is applied. So according to the right hand rule, the direction of this torque will be in this direction, T. Okay, so let's apply the reactive torques in the opposite direction of the net torque that has been applied to the bar. Okay, so this is TQ, this is, let this be TP. Okay, PTQ. Now draw the free body diagrams of this bar. So this is TP, TP, and for bar TQ, this is for bar PT, this is for bar TQ, it will be TP in this direction, and torque of 150 Newton meter in the opposite direction that has been applied. So this is the FBD of both the bars. Okay, angle of twist, the sum of angle of twist for bar PT and TQ is equal to 0. Okay, so sum of angle of twist for PT plus TQ is equal to 0. Okay, so theta is TL by GJ. So for I mean theta PT plus theta TQ is equal to 0. So that implies minus TPL GJ. Okay, due to sign convention I've taken this minus, plus 150 minus TP 2L GJ. Okay, let L be 100 mm. So if this is L, this will be 2L. Okay, is equal to 0. So when you solve this, this will be equal to minus TP is equal to minus 300 plus 2 TP, and that implies TP is equal to 100 Newton meter. Okay, and TQ is actually equal to 150 minus TP. Okay, because TP plus TQ is equal to T from this figure, and TQ is equal to T minus TP, and T is 150, 150 minus 100, so TQ is 50 Newton meter. Okay, yeah, Newton meter. So the option will be TPTQ, TPTQ, that is option C is your answer. Okay, always draw the FBD of each bar in these type of questions and you'll get the answer. It was a pretty simple question. Okay, thank you.